Okay, good afternoon and welcome back to the weekly live sessions on robotics and mechanics and control of robotic manipulators. We now head on to week seven lectures worth of discussions. Uh, so before we move on to the next, before we move on with this session, I would like to notice that I would like to bring this to your attention that there have been several errors or several mismatches for assignment sixes that has been pointed out during at the discussion forums, and this is just to ensure that we have actually taken some steps so that it will be more fair. I'm not sure whether the marks are reflected as per the measures that we have taken, but hopefully it will be reflected soon enough. Okay, moving on. This week we move on to the design and development of motion controllers of robotic manipulators. So until now, until week 7, we have discussed the fundamentals of robotic manipulators. Then we moved on to geometric modeling, where we solved forward and inverse kinematics problems. We then moved on to this kinematic modeling, which was useful for understanding the robot's singularities. And the robot kinematics will also have a reciprocal relationship with robot statics also, which is also very useful to estimate the forces required to hold a robotic manipulator in static equilibrium. And if you take the inertial forces into account, you will go one step further, where you will incorporate that is where you study the dynamics of robot. We have also seen some few common strategies for motion planning. We have seen the potential benefits and drawbacks of the various schemes, like straight line interpolation. We have seen cubic and quintic polynomial interpolation. We have also seen uh, trajectory generation using cycloidal trajectory. We have also seen a straight line interpolation with parabolic blends at the start of this trajectory and the end of this trajectory. So with that, further we will move on to control of manipulators. So this week's worth lectures is actually split on to 2 weeks. So in the next week, for 8 week also, we'll basically deal with a few of the topics. I think the cascaded control and all those things are actually being discussed in week 8. And in the lectures, we also see some MATLAB simulation on that front. So yeah, this was the general topics that was covered for the live sessions. A brief introduction and history of the development of robot motion controller was discussed. Uh, we have also seen different types of robot manipulator controls and their concerns. We have seen majorly two classifications of control. The first one being a kinematic control. Then we have also seen a dynamic control. Then further, we have also demonstrated some MATLAB simulation of various control schemes. So within the kinematic control, we have seen a scheme that is open loop and feedback based. Both open and closed loop schemes of kinematic control were discussed, and the same for dynamic control. We have also seen an open loop and closed loop interpretation of dynamic control. Both have their own advantages and disadvantages. So just to give a brief idea of motion controller, it's nothing but a subfield of automation. So automation basically requires a hardware, which is the robot itself. And to make it go through a set of points, a desired set of points, we need to make sure that the robot is actively uh, moving through that desired trajectory. If it is deviating away from it, some sort of corrective mechanism will have to be ensured or has to be deployed in a way that it is actually brought back to the desired trajectory. So it's just a subfield of automation encompassing the systems or subsystems involved in moving parts of machines in a controlled manner. So second point, a motion controller contains the motion profiles and target positions for the application and creates trajectories for the motor or actuators. So the motion profiles and the target positions, these are actually fed into the motion controller by the user. And what should it do with what should the controller do with the motion profiles and target positions? That depends upon the control scheme that has been designed. And later it will give its control signal to the actuator so that it can actually move the system, or in our case, the robotic manipulator, in a controlled manner. So why do we need motion controllers? Because essentially we have seen that we can essentially control a robotic manipulator just with a dynamic model. But on top of this, why do we need a motion controller? So like in robots, like just like any other engineering applications, it's impossible or it's very difficult to obtain entire dynamic model of the robot due to many uh, unavoidable reasons. So for example, throughout the course, we are familiar with the dynamic model tau as m of eta or m of zeta dot plus n of zeta dot. We are actually familiar with this model that has been discussed throughout the lecture. But in reality, this alone will not take the dynamics into account. We have a lot more terms that cannot be modeled. Maybe the effects due to gravity. We haven't modeled that in this equation. Then there are effects, the dynamics due to friction, viscous friction as well as Coulomb friction. Then there are, changes due to nonlinearities induced due to hysteresis. There are also nonlinearities due to material flexion, because throughout this course, we assume that the entire mechanism is actually made of rigid bodies, whereas in reality, that is not the case. So there are a lot of unmodeled dynamics, that actually comes in a real system, which cannot be actually modeled. And also there are things that we cannot 100% estimate. This mass matrix, the consistent elements in the mass matrices, which actually is a function of the mass of each of these individual bodies, as well as their moment of inertia. Neither of those could be accurately estimated in real life. And there are some situations where the parameters, uh, the constant parameters, which we consider it to be constant, changes with respect to time. Maybe for example, in case of mass, due to some environmental effects, it can accumulate more mass or it can lose more mass. All these things cannot be taken into consideration while we are modeling. Then the further necessity is the presence of external disturbances. So apart from model uncertainties, we have external disturbances and parameter variations, and which are inevitable in robots. So like for example, if you are actually moving a robot uh, uh, through a desired trajectory, maybe if the support is not fixed, that can probably induce some support induced oscillations and vibrations. And if it encounters some obstacles within the workspace, that could also be considered as an external disturbances. Or if lots more external disturbances, even airflow, a change in airflow can be also considered to be an external disturbance. So these actually makes it necessary. This actually makes it a necessity to design controllers without which we cannot control robotic manipulators. So like a dynamic model, just with a dynamic model, if there is any deviation on any of these parameters, and due to the influences of unmodeled dynamics, the robot may not actually track the desired trajectory, that it is intended to. For example, in the case of an inverse dynamics problem, we supply the desired trajectory, and we will get the torque required to realize this desired trajectory, and we supply this torque to these motors. But due to the uncertainties in the parameters and due to these external disturbances, we will get a different torque, and hence our robot probably will not, track the desired trajectory. And that is where this motion controller comes. It keeps on monitoring our desired trajectory, and it also monitors its actual trajectory using sensors. And comparing this desired and actual, comparing the error between the desired and actual trajectory coordinates, it will the controller will give appropriate control signals to the actuators. So yeah, these are also a few things that we have actually glanced through the lectures. I am just skimming through all these things because it could be beneficial for the it could be beneficial actually for the quizzes, for the tutorial sessions. So yeah, earlier this is basically the evolution of motion controller schemes that have been deployed on robotic manipulators. So until mid 70s, we mostly relied on exact models. For example, people could consider the dynamic model to be an exact model of a robotic system, and we relied on this dynamic model to control a robot. So yeah, we can only hope that the robot is isolated, it is free from external disturbances, and we have estimated the parameters to the highest accuracy possible. And there were no sensing actually. And that was that is what we call this classical motion control paradigm, or classical robots, where we only use exact models and no sense. And just to give a brief overview, a typical control loop would look something like this. It applies for any system actually. So we have over here a controller. So controller will basically act on the signal that it receives from one end, and it will give the control signals, maybe for example tau, to the plant, or for example in our case we can consider it to be a manipulator. And whatever signal that we are obtaining from this manipulator, it can be we can actually estimate what are the signals that is coming from out of these manipulators using sensors. And whatever signal is coming from the sensors, we usually call it as feedback signal. And yeah, we can actually compare our feedback and our desired trajectory. Maybe we'll call this as eta desired and eta actual. Right? And the error between the desired and the actual would be given onto the controller, and controller will give the appropriate the control signal to the actuators. So this is how a typical control loop would look like. And in earlier case, we did not have this part. In the classical robot scheme, it was only a feed-forward network without having any feedbacks. So then we go for this reactive paradigm that evolved during mid 80s, where there are no models. We purely rely on sensing actually. So we completely discarded the influence or the impact of a model, and we fully relied on sensors. So for example, if you take a look at this PID control, you can maybe call this as a fully reactive control scheme, where the control output of the controller is nothing but the proportional integral and derivative manipulations of the error signal, and we don't have any parameter that is coming from the robot's model. So that is what we have. What we call this reactive paradigm, and it heavily relies on good sensing, but there are also several drawbacks that are associated with reactive paradigm, in a way that it is very sluggish actually. So it depends on how you tune these PID gains. It can be very fast. It can be, it can more or less predict the errors very fast. But it will be actually a bit difficult if you to correctly tune this PID gains. all in all, like it's much more sluggish. The error tracking basically becomes a bit sluggish if you are only relying on pure feedback or pure only on sensors. Then later on, we have a hybrid scheme where we have a model-based scheme at higher levels and a reactive schemes at lower levels. So model-based schemes at higher levels means a model-based schemes where a model can actually be influential. For example, you can use a model-based schemes at manipulator level, and you can actually use a reactive scheme, probably a PID scheme or something, which is purely based on feedback on the actuator level. So on a manipulator level, you can use a model-based scheme, and at actuator level, you can actually use a feedback-based scheme. And then during the mid-90s, we have this probabilistic robots where it becomes a seamless integration of models, sensing, and this actually came after the realization that the models are always going to be inaccurate, because no matter how accurate our measurement capabilities are, there is always going to be some uncertainties in estimating the model parameters. And our sensors are also not 100% perfect, because there's a lot of noises that is associated with sensor measurements, sensor readings. And if you're using multiple sensors for measuring the same thing, they can have some sort of interference amongst them. You can also call them as sensor aliasing and all those. So in probabilistic model, there is a lot of assumption still going on, where we assume that the errors or the disturbances actually follow some probabilistic distribution, and then we actually do some manipulations with those actually. Then later we have this data-driven or data-driven or learning driven or learning-based control schemes, which is quite recent actually. With the fast development of machine learning and all those applications. So the reason I've said is that because these could come to your quizzes actually as probably match the following, or probably to fill in the blanks. If you are given this statement, what would be the correct control scheme? That could be a question actually. Okay, so that is about the evolution of different control schemes for controlling robot manipulators. Then we actually move on to the topic of robot motion controllers. So which basically starts by discussing the steps in involving design of a motion controller. So the basic steps to get into motion controller is to familiarize with the physical system under consideration. So in the case of a robot manipulator, how can we familiarize with this robot system though? So the easiest thing is actually the forward kinematics in case of serial robots, right? Because it becomes a wholly different story in a parallel robot, because solving for forward kinematics in parallel robot, it's much more difficult. But in serial robots, it's much more easy. You can use the algorithmic procedure of this DH convention. You can actually have this entire set of transformation matrices, and if you multiply the individual transformation matrices, you will ultimately get the forward kinematic model. And if you simply try and play with the joint variables, you can see how the robot actually moves. Even if it is very very difficult to visualize, you can actually plot based on the DS parameters, how changing each of these joint parameters causes the robot or manipulator to move. So once you get the geometry of the robot, you can actually solve the inverse kinematics problem, if you can exploit the geometry of the robot manipulator, inverse kinematics. Or you can also use some numerical schemes. It may not be always ideal, but if the inverse kinematics problem is far too complex to be solved analytically, you can always resort to some numerical schemes, which will always, most of the time, it will converge to a solution. So after that, if you familiarize with the robot manipulator, you start modeling, the comprehensive kinematic modeling. Then after that, you move on to the dynamic model, which is very essential for designing a robot controller. So by modeling, we first model the kinematics, then we move on to the dynamics. Then we also need to we also need to lay out our desired control specification. For example, how fast you want your error to, decrease, or how fast your error want to asymptotically go to zero, or what should be your steady state error. All these things comes under your control specification, or how fast, what should be your overshoot, error overshoot. Should there be any overshoot at all? Should there be any steady state error? All these things comes under control specification. So yeah, that is the first steps in designing a control, a motion controller. Then after that, we move on to objectives actually. So while we are designing, we have to make sure that several objectives are taken care of. So the first and foremost and the most important objective is the stability of the controller actually. So if you are obviously if the robot's controller is not stable, improper choice of the controller gains, it may actually lead the robot, or it may actually cause the control signal to be increasing exponentially out of control. And it may actually, it may actually blow up to, a magnitude that is actually very detrimental or very harmful for the robot. The another step is either regulation or tracking. So it basically means if your robot is currently in a position, and if your robot actually wants to move to a desired location, it should do that successfully. That basically is called a regulation problem, right? Forcing your current state to your desired state is actually a regulation problem. Or if you have to do that as a function of time, you have a series of points as a function of time. And if you want your robot to, move through each of these points at a specific point of time, that problem actually becomes a tracking problem. Regulation is actually not a function of time. You only need to go from your current position to your final position. And then later optimization, right, generally involves selection of optimal control parameters. It depends on the type of controller that you're implementing. So the important point is the most important thing, or the most important objective that you should be taking care of while designing a robot controller is the stability of the controller itself. Okay, so what are the types of robot manipulator controls and what are their concerns? So yeah, the broad classification, one of the broader classifications of robot motion controller are, it could be motion-based control, what we have seen earlier, for example, if you have this dynamic law, m of theta dot plus n of theta dot plus maybe a gravity term g of theta, whatever you can model. So, this is basically a motion. Sorry, I think this is the opposite, I think. I'll move this to here. So motion, a good example for this motion-based or model-free controls are the well-known PID control or PI control or PD control. So it purely relies on feedback. There are no model terms on it. So like, for example, if you can probably design your control or your input torque to be, maybe some Kp multiplied by acceleration plus Kd multiplied by velocity and Ki multiplied by acceleration. position. Or in that well-known convention, you can actually use is that Kp would be dou eta dot by dou t plus Kd multiplied by eta dot plus Ki into multiplied eta dot dt. You could consider this to be your control law. But as you can see, there is no influence of model in this sort of control law. There is no mass matrix or inertial elements or gravity terms. Nothing is actually there. It's a purely motion based or it's a purely reactive control law. So the advantages of this is that this is purely feedback and it's purely sensor based. So the control law is purely based on its motion, because depending on the motion, these terms actually varies. If it is accelerating, this term also increases, things like that. But it is also sluggish, and also it produces poor tracking performances, right? Because as you can know, the control law probably it need not be purely relied on motion. There are a lot of other things that can actually make it improve. So, like for example, if a robot has more inertia to move along one coordinate, and it has lesser inertia to move along the different another coordinate, using these sort of laws will not help in the robot's performance. It gets more sluggish to move in a direction which it has more inertia, and it can be more fast or more jerky in a direction which it has lesser inertia. So we cannot exploit these terms actually. Like if you know that it has lower inertia along one direction, we cannot use that to our advantage. We cannot use that to our advantage. So in that regard, it actually is sluggish, and it also produces poor tracking performances because the lack of model parameters in the control model. And what about model-based control schemes? So they are comparatively efficient and simple. A purely model-based is actually efficient because we don't need to rely on sensors. We can control it purely based on the model. If we have that model. And the drawback is that the accurate model should be available. So a model that is as close as possible to a real system should be made available. Otherwise, the tracking or the converging to a desired trajectory will not be really possible. So those are the standout terms for motion-based and model-based control scheme. So motion-based are actually easy to use because you don't have to derive dynamic models of complex robotic systems. But if you know the dynamic model, if it is a simple robotic system, and if you have the dynamic model, using a model-based control schemes, can be more beneficial. But obviously, the correct choice is, using a hybrid scheme, because one cannot be a substitute for the another. Okay, so then there are other types of classification where the robot control systems are either classified as robust control or adaptive control. So we use robust controller where we know the robot's model accurately, and we also know the bounds or the range of disturbances that the robot actually can have. So, for example, if you consider the dynamic equations of motion of robotic manipulator, we always assume that the constant parameters are always going to be constant. For example, the masses of each of these links and the moments of inertia, the center of gravity, all these things are considered to be constant in robust control. And we also have some sort of an estimate for the external disturbances that our system may face. So with that information, it is possible to model a controller even with these external disturbances, our robot will provide satisfactory tracking performances. But in case of adaptive controller, uh, we implement adaptive controller where we where the estimation of the parameters of the model is no longer possible. It's no longer actually possible because it varies as a function of time. For example, if you consider an airplane, its mass actually changes as it goes through its journey because due to the loss of fuel, because of the burning of the fuel and all those things. The lot of parameters that we considered constant earlier, it's actually a function of time. And we also don't know the extent of the uncertainties that we probably also don't know the extent of or the bounds of uncertainties that a system may face. So in those circumstances, we go for adaptive controller where it actually observes the real states in real time, and it actually decides the appropriate control parameters on the go, right? In case of motion controller, everything is constant. The control parameters are constant. The system parameters are constant. But in case of adaptive control, that is not the case. So yeah, again, a different type classification of robot motion controller. You can classify them as kinematic control, where you only consider the kinematic models are used. Like for example, you can because kinematic model is obviously very easy to model compared to a dynamic model because it involves a lot more computations. And you can probably use this kinematic control when your robot is moving very slow, where the effects due to this inertia can be more or less neglected. Or if the properties are not, very influential on the robot's final performance. And you can have two different schemes of kinematic control, which is open loop. You can have an open loop scheme, and you can also have a closed loop scheme for kinematic control. And in dynamic control, where the robot dynamics and the actuators are also taken into account, where you also consider the motions due to the effects due to inertia as the robot moves. And then we have a hybrid scheme, which is what we call a cascaded control, which has an output, an outer loop, an outer kinematic loop, and an inner dynamic loop. So we'll discuss the cascaded loop and its working in the during next week's lecture. But this week we'll mostly restrict our topics on kinematic and dynamic control. So here as well, in dynamic control as well, we have two schemes, open and closed loop schemes. Okay, so yeah, moving on to further classification, we can also classify um, the manipulator based on the type of interest or the type of application, which are motion or position control, where the output is only to control the final position of the robot. If you also want to control the force output of the robot, you go for this force control. For example, if you want to grasp something with a desired force, or if you want to twist something with a desired amount of torque, you would go for this force control. Then there are other cases where you have this hybrid control, where it is both force and position control, and also this impedance control, where it basically translates, or it basically transforms a force input to a motion output, or a motion output to a force based input, based on how you want to tune your robotic manipulator. Then there are other classifications. You can design a controller on joint space. You can also design a controller on task space, or even in sensor space, or even in actuator spaces as well. So I'm not sure if there is any advantages of either of these things, but I think it's mostly related to convenience, especially in these two cases. So next topic could be types of robot manipulator control and their concerns. So yeah, you can also, just like I mentioned earlier, you can have a regulatory control where the trajectory is not important. Your only objective is to move from your current position to a desired position, as efficient as possible. You can call this as a set point controller, where a constant reference input velocity vector is provided, right? So at all the time, this will be your reference, and you want your actual position to converge to your reference. But in tracking controller, your reference input is actually a time varying vector, because if you are here, your reference would be this distance, and if you are here, your reference would be this distance, and it keeps on changing with respect to time, because you need to reach each of these individual positions at a particular time. The trajectory influence is also there in case of a tracking control. Okay, so now we move on to different control schemes. So the first scheme that we would be investigating would be different schemes of kinematic control. So yeah, the first scheme that we would be discussing is an open loop scheme. We call this as an inverse differential, or you call this as an open loop control input. So what are the key features of this scheme? So in case of an open loop kinematic control, your objective is you will be having a desired joint positions. You'll also have a desired joint velocities. So these are all given in task space. You can also define your desired trajectory end effectors position also in task space also. These are in joint space. These are in task space. So your desired positions and your desired velocities. And we have the robot's Jacobian available because we can derive the robot Jacobian based on the robot's configuration. And our objective is to find out the control input or the control velocities that we would be giving onto the robot manipulator. So for example, from the point of view of a 2R robot, so this is the first joint, R1, this is the first joint, R2. I call this as this end effector. The coordinates of this end effector can be named as X and Y, and the joint variables can be named as Q1 and Q2. So your inputs in this case, or the control inputs, would be the joint velocities, Q1 dot and Q2 dot. Those would be your inputs. And your objective is if you want the robot to move through a desired trajectory, maybe X desired of t, Y desired of t, this is your desired trajectory. What should be the velocities that you should be giving onto these motors? Q1 dot t and Q2 dot t. That is your ultimate problem. So from the differential kinematics, we actually know from kinematics that this Q dot is J of Q inverse eta dot, right? Where this J of Q is the Jacobian matrix, and eta dot is the task space velocities, and these are the joint space velocities. So with this law, if you want your robot to move through a desired trajectory, eta desired dot, and you have your Jacobian matrix, because you can basically derive the Jacobian matrix depending on the geometry of the robot. Then your control input to the motors Q dot is nothing but J of Q inverse multiplied by eta desired dot. J of Q inverse eta desired dot. That is what is possible. That is what I have actually written here. The control input that you give onto these actuators. This is actually a vector. Q dot is Q1 dot and Q2 dot. Okay, so this is the control scheme that we would be implementing. And where or when does this control scheme work? So this control scheme will only work if this mu desired dot is not zero, right? If mu desired dot is zero, or if it is not a tracking problem, if the change of velocity as a function of time is zero, then Q dot is also going to be zero. There is no control input that we can give onto the robot. So eventually it will stop somewhere, because if mu desired dot is zero, Q dot is also going to be zero. So that is the first condition. And another condition is that this mu desired dot at initial time should be equal to the actual mu. So the initial position mu desired at t equal to 0 should be equal to the actual position at t equal to 0. Right? Otherwise, so basically what it says is that this mu desired dot and mu dot should be equal to 0. For example, how can I make this more clear? Yeah, so suppose this is the mu desired dot I'm drawing as a function of time. So this is mu desired dot at time equal to 0, and this point. And this point over here would be mu desired dot at the final time, right? And if your actual position is somewhere else, mu desired at t equal to 0 is somewhere else, based on this control law, the robot will track a similar path compared to the desired path. There's an S-shaped curve here. So based on the robot's properties, it will also path a similar curve like this. Mu desired at t to tf. So, but there is always going to be an offset between the desired and actual path. Right? So in order for this to not happen, the initial mu desired and the initial, so the initial mu of the desired trajectory and the initial mu of the actual trajectory should be coincident. Both of them should be starting from the same point. Only then the actual robot can track the similar trajectory to the desired trajectory. So that is this condition. The first condition says mu desired dot is not 0. That is this one. The second condition says the initial position of the desired trajectory. Yeah, making a mistake here. Yeah, so this is desired trajectory. This is actual. So the second statement, mu desired of t equal to 0 and mu of t equal to 0 states that the initial positions of the desired and actual should be coincident. They should go over here. Then only it'll be able to accurately move through the desired trajectory. So if both of these conditions are not satisfied simultaneously, then the inverse differential kinematics will not work. So I've got a question. What is the difference between the desired velocity q dot is not clear. What a difference between desired velocity and q dot? Are we saying that if the velocity of, say, velocity of 10 meter per second and the desired velocity will be 15 meter per second, so we can only achieve a displacement of 10 seconds. I'm not sure what I understood your question. So are you talking about this term?
Sir, Q dot and Q. Q dot and QD dot.
Okay. Q dot and QD dot. This one, these terms.
Yes, sir.
So the thing is that this QD dot will be obtained from this law. Whatever you are obtaining from this, if you are supplying mu desired dot onto this equation, what you are getting is Q desired dot.
Okay.
But that is how your that should be your desired robot's trajectory. That coincidentally that is also your input to your robot.
Okay.
Right? But in actual situation, your mu, for example, your robot is at probably, if I give this mu as x and y coordinates, it could be 10 and 12. But your desired trajectory, mu desired of xy, starts from maybe 15 and 20. The actual position is different from this desired position. So if you are actually trying to implement this open loop control scheme, when your initial positions are not matched, the actual position and the desired position, the initial positions are not matched, the robot will not, it will not go through the desired trajectory. That is what I meant. That is actually what I meant with this.
Okay.
Because the thing is that the general law is
Desired means you can say calculated.
Yeah, because the general control law is Q desired is J of Q. Sorry, Q dot is J of Q mu dot. This is the general law, right? Like forget about the desired parameters, right? But we have the desired parameters. We have the desired positions and we have the desired velocities. So what do? We simply plug into this kinematic law, into this kinematic equation. We simply substitute instead of this mu dot, we simply substitute mu desired dot. We can do that because it still is valid by the law. We can still supply into this thing. So if mu desired is supplied into this q desired is what we should be supplying onto the robot, or this q dot is what we should be supplying onto the robot, so that the robot will be able to track the trajectory. Right? Okay. And this will only track the trajectory. This will follow the desired trajectory. It will have the desired velocity, but it will not have the desired position. That is what I wanted to say.
Okay.
Yeah. So it will only go through the desired positions if the desired initial coordinates and the actual initial coordinates are matched. Otherwise, there will always be an offset between the positions. But the velocity will be the
But
same.
here R is there, na sir? R, either or the condition provided.
No, there is no or. This one,
after the condition R is there, na sir? So
no,
that means
this is either in joint space or either in task space. Both are.
Yes, sir. Yes, sir.
So these are the conditions actually. This is condition 1. This is condition 2 for task space. This is condition 1. And this is condition 2 for task space. So These are
Okay.
for joint
In the
space.
in the second line, and is missed, sir. So that's why we
Yeah.
understood that in the second line there is no and.
Yeah, there is a, that's my mistake actually. There should be an and here actually. Yeah, I hope that is now clear.
Yes, sir.
So this is now condition 1. This is condition 2. These two comes under condition 2. So in essence, the inverse differential kinematic law will only work if these two are satisfied. Otherwise, it will not work actually. Okay, so next is actually a closed loop scheme. That is, but it's still a kinematic scheme, but a closed loop scheme. So what I meant by this is that your control objective is, we first state the control objective. We want our system to be asymptotically stable. Like for example, if you can recall, we always say that our most important objective is stability of the robot. So here, the stability basically means as time tend to infinity, the difference between the the actual position and the desired position will be 0. Q desired tends to, Q tends to Q desired, or Q desired minus Q should tend to 0 as time tend to infinity. So if that is our requirement, how can we design our motion controller? So, so the easiest thing is that if I define this variable Q tilde as the difference between Q desired and Q, where this Q desired is nothing but the desired positions. So this is the desired position, and Q is the actual position. I can call this Q tilde as the error between the desired and actual position. And if I force the Q tilde, maybe Q tilde t as e raised to minus lambda t, if I want this error to behave as per this law, then we can say that the system is asymptotically stable, right? Because as t tend to infinity, Q tilde of t tend to 0. So like if we can somehow force our system to behave as per this control law, it is more or less guaranteed that the system is stable. Right? How can we do so? So the key thing is that if we somehow make the system to follow this control law, we can actually guarantee that the system is actually asymptotically stable. So in order for us to do that, what can we do? If you take the derivative of this equation, Q tilde dot is would be minus lambda e raised to minus lambda t. So this is nothing but minus lambda Q tilde of t, right? Because this term is nothing but this equation. So what can I write? Q tilde dot plus lambda multiplied by lambda Q tilde t will be 0. So this is a first order differential equation whose solution is something like this, right? So if I simply, instead of this Q tilde dot, so Q tilde is nothing but Q desired minus Q. So if I take the derivative of this, Q tilde dot would be Q desired dot minus Q dot. So if I substitute this onto this equation, you will get Q desired dot minus Q dot plus lambda q tilde t should be 0. And if I take this to the other side, I would get q dot is, q dot is q desired dot plus lambda q tilde t. So this will be your control input. And this is a feed forward term, right? If you want your robot to move a desired trajectory, maybe mu desired and mu desired dot, maybe using this inverse kinematics, you will get q desired and q desired dot. Because we have the robots model, we can obtain this q desired and q desired dot. That comes over here. We call this term as the feed forward term. And here we have q tilde. That is basically the error between the desired and the actual position. So this term, since it also has a feedback term, we call this as the feedback term. So in essence, if this is your control law, if you give this input to your actuators, if you give this velocity input to your actuators, you can more or less guarantee that the system becomes asymptotically stable. If this is your input, your system will behave like this. So a behavior like this basically means that as time tend to infinity, q tilde dot tend to 0. So I hope that is clear. So that is what is about robot kinematic motion control in joint space. And this is a closed loop control. So earlier case, it was an open loop, and we say it will only work on certain conditions, but this is actually a closed loop control. Okay, so that is about it. And yes, on a similar note, we also have this dynamic control actually. So dynamic control will also have an open loop control as well as a closed loop control. So the first one, what we have over here is what we call this inverse dynamics control. Inverse dynamics control is actually an open loop control. Right? I think I may have forgotten to mention this. So in the two velocity schemes that we considered, the first is actually called this inverse differential kinematic scheme, that is an open loop scheme, or it's also called a feed forward scheme because there's no feedback term involved. And the second scheme, we call this a closed loop scheme. There is also another name for this scheme. It's called, I'll write it over here. It's called the computed velocity control. Computed velocity control. This is a closed loop. So similarly, in the case we have open loop and closed loop in dynamic control. The first one is called inverse dynamics control, where a general robot control law, dynamics law, is given as tau would be m of q double dot plus n of q dot. So what do we have in our hand? We have the desired joint positions, we have the desired joint velocities, we have the desired joint accelerations. We have the inertia metrics because we can, by now we know how to derive the dynamic model of a robot. So we have the inertia metrics, we have the centrifugal and Coriolis effects metrics. So our objective is to find out the control input torque so that the robot, tracks this desired trajectories. So the simplest thing to do is that, instead of this general equation, instead of this q dot and q double dot, we can simply plug these into this equation. So our tau would look like m of q desired double dot plus n of q desired dot. Simple as that. There is no feedback term involved. We simply plug our desired coordinates into the dynamics equation. So, what are the problems actually? What are the problems associated with this? So, this scheme, again, like in the previous case, will not work if q desired double dot is 0. Right? If this term is 0, this entire term becomes 0. So tau becomes this term alone. So that basically, cancels a lot of terms in the dynamic model. So it will not work if it will not track a desired trajectory if q desired dot is 0 or if the accelerations are 0. And similar to the velocity open loop, we also have these conditions. The initial position q of t equal to 0 should be equal to the initial desired position q desired at t equal to 0, and initial actual velocity should be equal to the desired velocity at time t equal to 0. These two conditions will also have to be satisfied. Then only this inverse dynamics law would work, because it's an open loop. So the simple intuition is that if there is a person at xy as xy coordinates as 5 and 0, and if you want your person to move to 5 comma 0, this is your initial position, and if you want the person to move to 8 comma 0, you would simply give a control input of 3 comma 0, right? But what will happen if your initial position is actually some other place, 6 comma 3? So if you give the same control input 3 comma 0, your position will the person will end up at 9 comma 3, right? The movement will still be the same, but it will end up in a different position. So that is the reason why the initial positions and velocities have to be matched. Otherwise, these sort of things will happen for this open loop inverse dynamics law. So similar thing can be said about this closed loop law, where our objective is to find the dynamic control. So in this case, we call this the robot dynamic control. This is also a closed loop scheme. Closed loop. So just like earlier, we have the desired position coordinates. We have the desired velocities and desired accelerations, right? And what do we have? We have the actual positions as available. We have the actual velocities as available, because these are available through the sensors from the feedback. You also have the mass metrics, because from the dynamic model, you also have the vector of Coriolis and inertial effects. And your objective is to find the control. So you need to find the control law to satisfy the following objectives. And the objectives is asymptotic stability, just like in the previous case. As time tend to infinity, the position errors will tend to 0. The velocity errors will also tend to 0, where the error is defined as the difference between actual and desired and actual position, and velocity error is desired and actual velocities. So how do you do that? If you force your robot to move as per this governing equation, if this is how your robot's governing equation, what will be the solution of this equation? It will look something like C1 e raised to minus lambda t plus C2 e raised to minus lambda 2t. This will be your Q, right? If your robot is behaving as per the second order dynamics, the error, sorry, this Q tilde, the solution, the homogeneous solution would look something like this, a generic form. And yeah, if this is how your error behaves, what does that mean? So as time t tend to infinity, both of these terms will tend to 0, right? Because this is something e raised to minus infinity. Both of these terms becomes e raised to minus infinity. And as time tend to infinity, both of these terms will go to 0. And as a result, Q of tilde goes to 0. And with that, we can actually say that the system achieves asymptotic stability. So if this is how we want the system to behave, I'll simply replace this Q tilde by these terms, right? Q tilde is nothing but Q tilde double dot is Q desired double dot minus Q double dot. But from the robodynamics, we have this equation from any robodynamics. And from this equation, I can find this Q tilde double dot, Q double dot. And this Q double dot is this one. It is nothing but a simple rearrangement of equation 3, right? Take this to the other side and multiply it with M inverse, you will get this equation. And if you substitute this equation onto this previous equation, you will be able to get a final equation on this control input torque, this torque. This is nothing but this mass matrix M of Q multiplied by Q desired double dot plus lambda 1 Q tilde dot plus lambda 2 Q tilde plus N of Q tilde dot. So you can call this as the feed forward term, just like in the earlier case. And we have two feedback terms, because this is basically, these are basically difference between actual and desired. So those essentially involve some feedback terms. And this is actually what you call a feedback linearization term. So if you supply this torque, these joint torques onto a robot, you can basically guarantee that the robot will follow this second order aerodynamics, which translates to the system to be asymptotically stable. So you also call this control law as computed torque control. Computed torque control, and this is also closed loop control. Yeah, so there is also one more scheme that we can discuss in more detail, maybe during the next lecture. That is what we call this cascaded loop or cascaded control. So which has a kinematic loop at the outer loop and a dynamic control at the inner loop. Okay, so with that, we'll solve some sample questions, which maybe you can expect similar questions for this week's tutorial. So these are mostly descriptive, actually, for control, because most probably there won't be any numericals. It'll be mostly from the lectures. So the first question is, it's a true or false question. So it states whether the statement is true or false. The statement is a robot is not only a mechanical architecture, but it is also slaved by controller that impacts its performance. So it's a very generic statement. So I suppose we can all agree that it is a true statement, right? Without any ambiguities, right? Because what a robot should do is actually fully determined by the controller. Yeah. So answer is indeed true. Moving on to question 2. It's easy to obtain an exact dynamic model for robotic systems. The keyword is an exact dynamic model. Is it always possible? No, it's not really possible, right? Dynamic models are possible, but with some approximation, but not always an exact model. We cannot always have an exact model, right? Because there is always a lot of dynamics that cannot be even modeled, due to hysteresis, due to material nonlinearities. Then what else? We haven't even covered friction in this course, friction, then what else? Backlash. All these things cannot be modeled. And there could be external disturbances also. Those things also cannot be modeled. And this is, it is exactly due to this reason that we have motion controllers, because we cannot always have an exact dynamic model. So, yeah, I think it could be tricky, because the question is more or less tricky, because we actually derive dynamic model throughout the course, but it's only a very simplified approximation. It's never a representative of an actual system, where it has a lot more factors that can affect its dynamics, but which cannot be easily modeled. So in that regard, this statement is false, I believe. So yeah, if you have objections to these sort of questions, you can always raise this in the feedback in the Google form, or sorry, in the group discussion. And if the concerned faculty also agrees, maybe these sort of questions may not be repeated. Okay, so moving on to question 3. If Q decide and Q decide dot are the desired joint positions and velocities, then the computed velocity control can be given as out of these options, where lambda is greater than 0. Also identify the feed forward term with the control law. So a computed control law should make the system, so computer velocity control should make the system behave as per this law. Q tilde dot t should be e raised to minus lambda t, right? So, or in other words, Q tilde dot plus lambda Q tilde should be 0. Or if you substitute the relevant values, Q decide dot minus Q dot plus lambda Q tilde, this will be 0. And yeah, so Q dot would be Q decide dot plus lambda Q tilde, or Q dot would be Q decide dot plus lambda multiplied by Q decide minus Q. This is your computed velocity control. So out of this, this would be the feed forward term. And this term is actually the feedback term. Right? You can write this control law in joint space, just like what I have written over here. And this can also be written in task space as well. I think we have seen the task space scheme in the previous slides. This is a joint space scheme. Okay, so in that case, which is the correct option? I think I'll go with option C. Yes. Option C is the correct answer. So yeah, now we move on to question 4. It says the expression for proportional integral controller with a feed forward term is, so it's a proportional integral controller. It does not have anything to do with model. So what is this? Q dot is, you have a feed forward term, you have the proportional term, which is proportional to the proportional controller action is proportional to the error in position. And the integral action is actually proportional to the integral of the position error. So I think option A itself is pretty much the correct answer. Or option B. Yeah, in option B, this is not the correct feed forward term. This is actually the feed forward term. Q decide dot. So I think for question 4, option A is the correct answer. What about question 5? So the computed velocity control is out of this, which is the correct answer. Is it a feedback controller? Is it a feed forward controller? Is it a motion based controller? Is it a robust control, adaptive control, optimal control? Motion based controller means it's model free, but obviously we have a model term coming here because we have a Jacobian term coming in terms of a computed velocity control. So that is not the correct answer. And these are also not the correct answers because we haven't discussed any of these cases in our course. That leaves us whether to determine whether it is a closed loop or an open loop controller. So the CTC or CVC Q tilde, sorry, the control input Q dot is Q decide dot plus lambda Q tilde. So as I've said, we have a feed forward term and a feedback term that makes this entire control law as a feedback control or a closed loop control. So in that regard, this itself is the correct answer. Because CVC also has a feedback term in it. So it's a feedback based or it's a closed loop control. So that's indeed the answer. Now moving on to question 6. So finding the time history of position, velocity, and acceleration for a set of input joint torques. It's called forward kinematics, differential kinematics, dynamics. Which of them is the correct option? So we have joint torque on one hand, and we have the trajectory on another hand. Q dot, Q double dot. So for a given torque, the problem of finding the trajectory is forward dynamics. And for a given trajectory, finding out the joint torque is inverse dynamics. I hope it's fairly straightforward. So in that regard, the correct answer is option C, forward dynamics. It's indeed option C. Moving on to question 7. If M of Q, Q dot plus V of Q, Q dot plus G of Q is torque, is the dynamic model of, if the dynamic equations of a robot manipulator, then which of these options are correct? So the mass matrix is a symmetric matrix. That is indeed correct. V of Q is not a symmetric matrix. G of Q denotes centripetal. That is also false. That is the gravitational term. G of Q does not denote the inertial term. That is also false. Option 5 is also false. Option 6 is also false. It's a fairly straightforward one-word question. It's option A. That is the correct answer. Yeah. So question 8, from the following choices, select the correct case that corresponds to motion-based or model-free control with gravity compensation. So it does not have, it should not have any model parameters coming into this control law. So all the things that comes with this mass matrix, we can eliminate it straight away. So we can eliminate options 1 and 2, 4 and 5, out of which the correct option would be, this is obviously not correct because Kp is difference between Q desired and Q actual. It takes the sum. This is the, obviously these are not the error terms. That leaves us with option C, because Kp is proportional to the error and Kd is proportional to the derivative of this error. So that makes option C to be the correct answer. Yeah. Moving on to question 9. I think we have solved this earlier actually, right? We have seen this problem earlier. And this is the correct answer for computed velocity control. So maybe we can modify this question. What about this inverse dynamics? Inverse dynamics control. Is it an open loop or is it a closed loop control? If that is the question. Because for dynamic control, we have seen 2 cases. The first one was this inverse dynamics control. And the second one was the computed torque control. And we have also seen how this is an open loop controller and how this is a closed loop controller. Okay, so in that regard, I think there won't be any ambiguities in finding out that inverse dynamics control is indeed a feed forward or an open loop control. Okay, so yeah, with this, that is about it for today's session. I think we can we wrapped it up earlier compared to last week. So if you have any further questions or further clarifications in any of the quizzes or assignments, please let me know.
Sir, I have a doubt, sir. I have a doubt. Sir,
Yeah.
whatever Vikram lander is there that is landed on the moon, whether we treat that as a robot or not?
Like, yeah, we can treat it as a robot, right? Why not?
That means you are saying that exact dynamic model is not possible.
Controlling those sort of things, it's much more complex because, dynamic models is possible because there are a lot of things that we can actually measure to a very close approximation. The mass and all those things, we can easily measure all these things. But, there are a lot of things that we cannot model, how we cannot exactly simulate the impact, the impact with which that lander is actually coming to the lander is actually, interacting with the moon's surface. We cannot exactly predict that, but we sometimes we may have some estimate. We may have some estimate, or the range with which the uncertainties can go. And if we are aware of that range, or if we can approximate that range of uncertainty, we can then accommodate that uncertainty into our model. We call those sort of things to be robust controls and all those things. But again, there are a lot of things that we cannot exactly model. Maybe the friction, or maybe some expansion, or some material changes due to these thermal radiations and all those things. Well, not a lot of things can be truly estimated, but as you can see, they have actually modeled everything to a very see, ultimately, it all comes down to whether your assumptions are valid, because all these things are assumptions, and you can simplify your model, provided your assumptions are actually valid, right? If you make your robot out of very rigid material, you can always assume that the element to be a rigid body. But if the robot is made of flexible material, you cannot apply this dynamics equations of motion, because it behaves like a continuum body, and rigid body laws are not at all suitable for that. So ultimately, everything comes down to the fact that how valid or how accurate your assumptions are, and with that you can more or less ignore a lot of effects. You can more or less ignore, or you can assume effects due to the unmodeled dynamics are negligible. And if that is the case, then more or less what we can actually model could be a very good estimate of the actual system. So yeah, I think that is my answer. But whether you can actually model a dynamic model or not, that a robot should not be based on whether you can have an exact model or not. So these days, even if you don't have an exact model, even if you don't have any dynamic model, you can still predict the dynamics using this machine learning techniques and all those things. So, still that does not make it not to be a robot. It still is a robot. So yeah, that is my answer.
Okay, sir. Thank you.
Yeah.
Sir, can I ask you one question?
Yeah, sure.
Sir, this week lecture is going at 180 kilometers per hour.
Yeah,
It's
our
very-
lecture, right? Yeah. I'm sorry for that.
Very
Yeah.
confusing. Okay.
But it's
Will it
mostly
be
theory.
possible? Yeah. I want you to do a favor. Can you go back to your PDF and
Yeah.
put two slides at a time? Like we have kinematics, some open and closed. Put both of them side by side. And can you talk of the difference? You're showing one slide per page now. Can you put two slides per page? This one and the next
Two
one, can you put them
slides per
side by side?
page. At the moment, I don't think it's possible. So I'm not sure if that is possible or not. Let me check. Yeah. Is this fine?
Right.
Yeah.
Maybe can they now instead of up and down, can you put left and right? Will that be possible? Or, it's okay. You see the desired quantities are
Yeah.
QDT, and here you got another some set point control.
Yeah. So you want me to talk about the two
What
different
is the
kinds?
difference between these two slides? And then talk with say kinematic control slide and then the dynamic control slide. What is the difference that is coming? I understood what is happening here to some
Yeah.
extent, but what is the difference between these two? That needs to be clear.
Sure.
You see
So
that available is Jacobian. Here also we see Jacobian matrix is available. Actual joint control input is also same.
yeah.
Looks like. And then the objectives here are
See, okay. I'll try to make it as intuitive as possible. So like we have these two governing equations actually. So if you only take a look at this kinematics, we know that the kinematics, the forward or inverse, either ways, you can actually have this governing equation eta dot as j of q multiplied by q dot. And for the dynamics, we have this equation or these equations of motion. The torque as m of q double dot plus n of q dot. Right? These are the two governing equations. Like if you are only considering the kinematics, you have this equation. And if you only have the dynamics, you have this equation. So the main the main feature of
no,
this
sir.
open
I'm trying to understand what
yeah.
difference will come between an open loop and a closed loop for
Yeah,
kinematic
so
control.
okay, so open loop is that like so what we actually want is that our ultimate aim is to guide our robot's arm to move through a series of points. So like
Okay.
for example, I hope you agree with that. If you have a 2-hour robot like this, and, yeah. So let this be the first joint. I'll label this as Q1. This be the second joint, Q2, and this will be I'll label this as eta1 and eta2. Instead of x and y, I'll just label this as eta1 and eta2. Because to make this clear that this is task space and these are joint space. So your objective is that you want your end effector to go through a series of points. You call this as a trajectory.
Okay.
Right? So yeah. So for example, if your desired trajectory is something like this, I'll call something like this. Something like this. This is your desired trajectory.
That means it is the actual.
Yeah, this is desired trajectory. And this is the start point of the desired trajectory. And this is the end point of the desired trajectory. So I'll label this as time t equal to 0, and this is t equal to f. Right? So so in any open loop scheme, what you do is that you simply plug in this trajectory coordinates into this equation.
Okay.
If you're only talking about kinematics, or you plug this trajectory coordinates into this equation. Yeah, into the dynamic equation.
Okay.
Straightforward.
Okay.
Right? So the thing is, if you're the problem with this method is that if your robot's initial position is here instead of here somewhere else, as per this governing equation, it'll actually follow a path that has a similar shape to this, but it'll do this somewhere else.
Yeah, that's what you have shown.
Yeah, it'll go somewhere else. So in order for this open loop schemes to work, you have to first make sure that the initial position of the actual trajectory and initial position of the desired trajectory should be the same.
Okay.
Like
That
this.
is when you are showing that QD
Yeah.
t equal to 0 and Q of t equal to 0.
Yeah.
Yeah.
Then only it'll be able to follow this trajectory. Otherwise, it will follow some other trajectory.
Okay. Then what is happening in the next slide?
In the next slide. Yeah, okay. In the next slide, you also have an additional requirement. And the additional requirement is this one. This is actually a very important thing. You want your controller to be asymptotically stable. Right? So the thing is that I'll also try to say one of the most important differences between these two schemes. So for example, assume that in this case, in the open loop scheme, your initial and final positions, your actual and desired positions initially are same, right? So as the robot tracks, it should theoretically follow the desired trajectory, right?
Okay.
But what happens, for example, if there is some disturbance or if due to some factor, the robot momentarily goes to some other point,
Okay.
right? And what happens further? It'll go like this.
Okay.
Right? It cannot come back to the desired trajectory.
Okay.
Right? So like earlier it is going like this. Due to some issue, it goes like this, but it cannot come because there is no feedback term, there is no error term. So it goes
Oh.
like this. Due to some disturbance, it goes like this, and it goes like this.
Okay, what you are saying is in the first slide you don't have a feedback term, and
You
in the
don't have a
second
feedback
slide,
term. Yeah. You don't essentially have a controller. You don't have, you don't, if the robot arm goes out of control, there is nothing to, guide it back to the desired path.
oh, okay, okay,
Yeah, it'll only work if these conditions are met, mu desired dot is not 0, and the initial, actual and desired positions are same, and there are no disturbances, nothing to disturb this robot arm. Then
okay.
only under this limited circumstances, this thing, the open loop schemes will work.
Oh, okay. Understood.
Right? Yeah,
Yeah.
this is true for
Because of this,
kinematics and dynamics. This is true for both kinematics and dynamics.
okay.
Right?
Oh, okay.
Okay, so in case of a closed loop case, in the case of a closed loop, I'm not sure if is it visible?
Yeah, it's visible, sir.
Yeah, okay. So in case of a closed loop, I think I should have made this clear in the first time itself. So in the case of a closed loop, you also have an additional requirement that you want your system to be asymptotically stable.
Okay.
So what that means is that if there is an error, any sort of error, so as time goes to infinity, the error should be converging to 0, or error should tend to 0.
Okay.
So like if you consider this example, if there is any error, so like if the robot starts from some other position, as time goes to infinity, it should converge to the desired trajectory like this.
Okay.
Right?
That happens in the closed one.
In the closed loop, yeah. If the robot arm is starting somewhere else, or if it is originally starting close to this, and due to some disturbance, it goes to someplace else. Eventually, as time goes to infinity, it should eventually converge to the desired trajectory.
Okay.
No matter what the cases, it should eventually come to this trajectory. So that is your requirement actually. As asymptotic stability is coming as an additional requirement.
Okay.
So how can you ensure that?
Okay.
So if you force your robotic system to behave as per this first order dynamics, q
Okay.
tilde dot plus lambda q tilde equal to 0.
Okay.
If you try to force your robot to behave as per this control law,
Okay.
this asymptotic stability is pretty much guaranteed.
Okay.
I hope that is clear because, this is a first order differential equation. So the homogeneous solution would look something like this. Q tilde of t is C, a constant, e raised to minus lambda t, right? So if this is how your robot is going to behave as per this control law, the solution of this differential equation is something like this. And as time goes to infinity, q tilde will go to 0. It is apparent from this solution.
Okay.
So yeah, that is pretty much the essence of it. So what do we do? Now we simply manipulate this equation. How can we manipulate that? So instead of q tilde dot, I replace that with q decide minus q dot. So I substitute this back onto this equation. I'll get it as q decide dot minus q dot plus lambda q tilde as 0. So in velocity level, we consider this q dot to be our input. The velocities that we supply onto these actuators, we consider that to be input. So taking this to this other side, what will we get? Q dot is q decide dot plus lambda q tilde. So there is always an error term actually. So, whenever there is an error, the controller will actually, give a control signal that is proportional to this error. In velocity level, it'll give a control signal that is proportional to this error, plus some feedback, so some feedback forward term to offset some of the initial errors.
Okay, sir. Clear, sir. This is clear.
Yeah. So yeah, this is about, so if you give this control law to these actuators, you can pretty much guarantee that as time tend to infinity, this error q tilde dot will tend to 0.
Okay.
So yeah, that is pretty much the case for this open loop scheme and closed loop scheme. And
Sir,
the
then
case,
what is the robot example for open loop and closed loop, sir? Which robot is an example for open loop?
in real life, an open loop scheme is actually not very suited. But when you talk about this mobile robots, if you consider this joystick operated mobile robots, you can pretty much implement it as an open loop scheme. Why not? Or if you want to create a robot for educational purposes, maybe a joystick operated robot just for this forward kinematic simulations, you can have it as an open loop scheme, right? Maybe a joystick operated or a remotely operated mobile robot, and it can be a open loop scheme. But if you want to have an autonomous mobile robot, which navigates on its own, then you need to have it as a closed loop control. Or if you want to have a robot for this pick and place application, it will have to go to this exact location to pick, and it will go to some other exact location to place. So for that, you also need some, for that you need this, what do you say? This closed loop controller. Teleoperation purposes, maybe, for surgical robots and all those things, probably you can get away with open loop. Because the feedback is provided by the operator itself. Right?
Can you
Thank
show the
you, sir.
difference in dynamic control, sir? No?
Yeah. Yeah, so just like the case, what I've said earlier, the dynamic controller will also have two schemes. So the
Looks like
dynamic,
it's the same.
yeah,
It looks like it's the same, whatever you are seeing, whatever you have talked there. The only
it's this,
difference there is
yeah,
in kinematics, we are talking at the velocity level and
yeah,
displacement level, whereas in dynamics, we are ensuring that acceleration doesn't go to 0.
exactly
And we
correct.
ensure that the velocities and positions are same.
Yes. That is the only difference. You will have one more variable actually. And here you want the system to follow a second order error dynamics. Earlier it was a first order error dynamics.
Right.
Now you
Okay.
have a second order error dynamics so that your system will be asymptotically stable. The positions will tend to 0, position error will tend to 0, the velocity error will also tend to 0. That is the only difference in case of acceleration.
Apologies, sir, for making you to
It's not a
repeat.
problem at all. It's not.
You told everything, but I could not catch it.
It's okay. It's my problem because I was also rushing through this actually. So
I was coming from this iterate numerical methods standpoint. I was looking at these equations and getting confused. There we see new result equal to old result plus some lambda times error. But surely
okay,
I'm
yeah,
seeing here velocity equal to new velocity equal to old velocity plus lambda times position. I was getting confused.
yeah.
What's happening here? Okay, that's
Yes.
how people have framed these things.
Yes, yes, yes.
Finally, for them, it is the position, not the velocity. That's why they are correcting it at the position level.
Position level, yes. A lot of cases are like that actually, especially in mobile robots. Most of the cases they'll simply stop with velocity control.
Okay. And in dynamic control, you also see that they do this correction for both velocity and position.
Yes, correct. Yes.
Okay, sir. Thank you. I understood.
Okay. Okay, so
That's all from my side, sir.
okay, thank you very much for attending. Anything else?
Sir, why in the subject the title is mm, robotic control and manipulator? Is it different from the robotics subject, sir?
Yeah, because robotics is quite vast, right? There are lots of robots. So the course title is Mechanics and Control of Robotic Manipulators.
Yes, sir.
We have mobile robots, right? Mobile robots which are not manipulators, which are locomotive devices. Manipulators are only to manipulate objects around it, but mobile robots like locomotive robots are used for motion of that robot itself, right?
So
that
here
is
the position is fixed, the base is fixed.
base is
Here.
fixed actually, yeah. And robotic manipulators, especially the dynamics and all those things, are much more involved in manipulators because there are lots of bodies in a robot manipulator. But in case of a mobile robot, the mobile locomotive device, the movable bodies are actually very less. Only that the base of that robot moves. Unless you have a mobile manipulator on top of it, dynamics of that mobile robot itself is actually, is not as involved as robot manipulators.
Sir, next time I need some 10 minutes class about the KUKA robot. Is it possible, sir? Will it come under robotic manipulator or not?
KUKA robot, yeah, KUKA robot is a robot manipulator, right? So everything we learned here, the DH parameters, if you want to see the kinematics of a KUKA robot, you need to do the DH model of a KUKA robot. You have to do that.
At least, can we have the introduction or at least 5 or 10 minutes next time, sir? Is it possible, sir?
Next time, I'm not sure because we have to stick to the topic. Maybe we'll also have one more lecture actually. Maybe after week 8 tutorial, we'll probably have one more final lecture. But what do you need to see about KUKA robot?
We have in our college the KUKA robot is there. Sir, I want to know its theoretical concept. So that's why I have registered for this one.
Okay, so a KUKA robot, maybe, yeah, let me check if it is possible. But the same principle applies there. You can, if you know where the joints are, what kind of joints are, we can have the DH model. And once you have the DH model, you can, maybe I can show a simulation, maybe probably if I have time, I can probably show a simulation of a KUKA robot, probably in MATLAB. Yeah, at least at the kinematic level, probably dynamics.
Okay, sir.
Yeah. Okay.
Thank you, sir.
Okay, thank you. So I'm winding up this lecture, okay?
Okay, sir. Thanks a lot.
Thank you.
Have a nice day.
Thank you. You too, Ashley.